Hello everyone. So I'm sorry that we had to start the class a little bit late today, just late by a few minutes. Uh, but yeah, so I'll start the session as soon as somebody joins in, and I'm just joining in from my other device in the meantime. So also, since this is the last class of this entire course, if you have any other kind of questions related to the syllabus, although we already have had a review session and everything, but if you still have any conceptual doubts, especially any conceptual doubts, please do ask me, because this is like the last interactive session we are having for this particular course. Okay, let's start the screen share. Okay, so today we'll start with bargaining game. It is kind of similar to what we discussed last time. It's not too complicated, but since we have, there are two topics to be covered today. One is bargaining, the other is perfect Bayesian equilibrium. So I'll take two questions on bargaining today, and the third question will be on perfect Bayesian equilibrium. And although these are only three questions, but perfect Bayesian equilibrium actually is a slightly abstract concept, so I want to give it a little bit more time and go over it a bit slowly. So that's why I've not kept too many questions, but rather just explaining a little bit more in detail. So let's see if anybody's joined. So, I'm just allowing a few minutes to people to join because I don't want them to miss out on what is being discussed. So just maybe 1 or 2 minutes, and then we'll start the class. So also for today's, for this week's discussion, I've referred mostly to Joel Watson, Strategy and Introduction to Game Theory by Joel Watson. And two of the questions we are taking today are from Joel Watson. Okay, so let's start the class. Today, the first question is on different payoffs in bargaining, wherein, even if the split between two players in bargaining, it may be y and 1 minus y, even in that situation, the payoff of at least one of the players is different from just y or 1 minus y. There is it's defined by some other function, right? So here in this question, this is from Watson, it says that it's an ultimatum game in which the responder's payoff, which means if player 1 is making the offer, then player 2 is the responder. The responder's payoff is given by y plus a times y minus z, where y is the responder's monetary reward and z is the offerer's monetary take. Means z is the offerer's quantity, what they're getting, right? And a is some positive constant. Okay, so here they're saying that the responder cares about how much money he gets, and he cares about the relative monetary amounts also. Relative monetary amounts meaning how much he is getting versus what the other guy is getting. You see, y minus z is the difference between the amount he is getting versus the amount the other guy is getting. So he cares about both the things, but how much he's getting, which is given by y in this. Let me annotate this. How do I annotate this? Where is that one? Okay, I'll annotate it in the slides. So this is the question basically, where yeah, 1 minute, I just saw it. Yes. So let's annotate this. So here we are saying that the responder, that is player 2, cares about how much he gets, which is y, and he also cares about some function of the difference between the payoff he gets versus, or the monetary amount intake he gets versus what the other guy gets. So if player 1 is getting quantity z and player 2 is getting quantity y, then y minus z here is the difference between their monetary takes. So player 2's payoff function is not simply y, it is y plus a times y minus z. And we're saying assume that the offerer's payoff is as in the basic model, which means player 1 is getting z. So we can just write this here. u1 is simply equal to z, whereas u2 is equal to this value here. Okay, and we are asked to represent this game in the extensive form, and we are asked to write the payoffs in terms of m. M here is the monetary offer of the proposer, meaning what player 1 is offering to player 2, and in terms of the parameter a. Now, of course, we have to find the subgame perfect equilibrium, and what is the equilibrium monetary split as a, the value, the parameter a becomes large. Okay, so I've just so far all I've done is explain the question to you. So this question is not like, it's not a difficult question actually, but it's just that the language is a bit tricky. You need to understand what they're trying to say in the question, in this particular question. So I'll write this down in a language we understand. So basically, all we are saying is that, say, suppose the split between player 1 and player 2 is, let's draw the diagram first. Say, suppose player 1 is the one who's acting first, and he's choosing some quantity between a range of continuous values. He's choosing some quantity m, which he's offering to player 2. This is player 2. And after he offers this value m, the player 2 can, of course, choose to accept or reject. Oops, sorry. Player 2 can choose to accept or reject. This is, say, he's accepting, this is rejecting. And if he accepts, his payoff is given by u2, the function u2, and player 1's payoff is given by function u1. Let's write this as u1 comma u2. This is the payoff. The payoff is not what we normally consider as the payoff, and this is 0, 0. Here, now we are going to define and write out the values of u1 and u2. u1 we are told is as normal. u1 is 1 minus m, and u2 we are told is what? Let me just open the function again. So u2 we are told is a function of this guy's payoff, which is m. Writing is really bad sometimes. M plus a into y minus z. Now y here is m and z here is 1 minus m, right? So y is m minus 1 minus m. u2 is equal to, this becomes m plus a into 2m minus 1, right? This is the function for u2. Now this is all there is to the game. So now we are asked to find what the equilibrium is going to be, what the subgame perfect equilibrium is going to be, and we are also asked to find what happens if a, the parameter a, is very large. What do we mean by when the parameter a is very large? It means that player 2 is giving a lot of emphasis to the relative quantity he's getting versus the absolute quantity he's getting. So what player 2 is actually getting is m, and this guy is getting 1 minus m, right? I don't know where to write this. This is because we have put this in u1 and u2, but you understand what I mean. Player 2 gets m, player 1 gets 1 minus m. So he is not concerned so much about just the value of m as he is concerned about the difference between m and 1 minus m. That is going to that is mattering a lot to him if a is very large. So first of all, let's see what the equilibrium is going to be. So we are obviously considering the simple model in which player 2 is trying to evaluate his options of this value u2 versus 0, right? We know that if he rejects, he gets 0, and player 1 also gets 0. So, and player 1 knows this, right? If player 1 knows that if player 2 rejects the offer, then both of them are going to get 0. So what is player 1 going to offer? Player 1 is going to offer him something which is just more than 0, so that player 2 is going to accept it, right? So player 1, therefore player 1 will offer a quantity m, just so that, not the quantity m, but the payoff of player 2, so that u2 is just greater than 0. Right? So far, this is the only difference in this game and the normal games which we have discussed so far, that in the normal games we considered the quantity m and 1 minus m, or the discounted version of that, delta 1 x1, delta 2 x2, and so on and so forth, and we compare that with 0, 0. Here we are saying that the payoff function itself is different, right? So in this case, what we get is u2 is greater than or equal to 0, or we find the condition in which it is 0, and which is m plus a into 2m minus 1 is greater than or equal to 0. So let's separate out the m terms here and the a terms here. This is m into 2a plus 1 minus a is greater than or equal to 0, which means m is greater than or equal to a upon 2a plus 1. So player 1 is going to offer some quantity m, which is just greater than this value, a upon 2a plus 1. So this is a subgame perfect equilibrium. Okay, now we have to find out the limiting case when A is very large. Okay, when A is very large, then say M is just equal to A upon 2A plus 1 or 1 upon 1 by A plus 2, right? Now limit, take the limit of A tends to infinity, or let's take this as like this. So, which this means that in the scenario when A is very large, the split is going to be such that both of them split half and half, right? Because when A is very large, the player 2 is attaching a whole lot of importance to the difference between their between their sums as compared with the absolute value. So in that case, it means that that difference will need to be zero, right? When A is very large, it means that um, all the importance is attached only to the difference, and hence if the difference becomes zero, they split equally, which is half and half. So this is sort of like a kind of an example of axiomatic bargaining, in which you see that the subgame perfect equilibrium comes out to be sort of like a symmetric situation when the parameter A is very large. Okay, so it's a simple question, but I thought it interesting, so I took this question. Any questions? Okay, so I'll move to the next question, and I think we discussed a similar kind of a question in the previous review class also, and there is like, of course, there is a lecture on this also. So this is a question which is simpler version of what you have in the lecture. In this, we are saying consider the following discounted 3-period bargaining game where the discount factor is delta for both the players. Okay, so that is, I think I forgot to type that out, but delta is the discount factor for both the players. So in this game, player 1 makes the first offer. If player 2 rejects this offer, then player 1 makes another offer. So remember, player 1 is making another offer. Player 2 is not making the second offer. Okay. If player 2 rejects the second offer, then player 2 makes the final offer. So first player 1 makes the offer, then accepts or rejects. If player 2 rejects, then player 1 makes another offer, right? This is a slight point of difference from the questions we have discussed so far. If player 2 rejects the second offer, then player 2 is going to make the last and final offer. In other words, player 1 makes the offers in period 1 and 2, whereas player 2 makes the offer only in period 3. So compute the subgame perfect equilibrium of the game. Okay, so I will, I will mute myself for a few minutes, and I will let you. Why isn't this going full screen? Yes, better. So I will let you first draw the extensive form game diagram and represent this uh, problem in the extensive form, and just think over it for a few minutes, not too long, just a few minutes, and then I will solve the game. Okay, so I'll just mute myself for a few minutes just to allow you to think, and then we'll come back and solve the question. Okay. Did you attempt it? Any solutions? Yes, I think you are correct. Let me just go over the solution also. So just for the record, like I also got the same answer what you got, and we'll solve it and we'll check if this is correct. But somehow because the notation used in some of the solutions for the book is different, some people are getting a different answer. So just wanted to warn you of that, because I checked the solutions also in case you go back to the book and check the solutions, that is. Okay. So I got the same answer as you, and I think it's correct. And we'll check it in the class also right now. Okay, so first let's draw the diagram and be clear about what we are referring to as X, Y, and Z. Okay, so the question says that in the first period, the offer is X. In the second period, the offer is Y. And in the third period, the offer is Z. So we will carry that notation forward in the whole game. So let's first draw the extensive form game. Ouch. Okay, so this is the. So what I'll do is I will write the payoffs in a different color for each stage of the game, so that it is not confusing. So let's start with period 1. Why am I drawing these horrible lines? So this is indicating that this is a continuous choice, and player 1 is acting here at this node, and he's offering X, right? Now after he offers X, player 2 acts at this node, and he has the option to accept or to reject, right? So player 1 is offering X, player 1 gets 1 minus X, and player 2 gets X, right? If he rejects, then player 1 makes another offer, right? And he again offers. It's very difficult to draw on this iPad like this. Just give me a moment. Let me readjust the screen. Okay. He offers Y this time. This is player 1. Okay. Player 1 is offering Y. And now player 2 again has the option to accept or reject. Okay, let me write this in a different color. Now player 2 is going to accept or reject. So here the payoff is going to be, the offer is Y made by player 1, right? So he's getting 1 minus Y. Player 2 is getting Y. Now if player 2 rejects, then player 2 is going to act at this node, and he's going to offer, what the hell happened here? I don't know why I suddenly think, but okay. Sorry, there's something wrong with my pencil actually. It's not need a new pencil. Okay, so here he is offering some value Z. This is Z. Okay, and this also is a continuous variable. And here player 1 is going to decide whether he accepts or rejects. And if he rejects, everybody gets 0. If he accepts, then player 1 gets Z, right? And let me write this in a different color. Z and 1 minus Z. Right now, so far I have just written the division values, but now we are going to add the discount factor also, right? So this is delta. Let me rewrite the whole thing again. Delta into 1 minus Y comma delta Y, right? And this is delta squared Z and delta squared 1 minus Z. So far, so good, I hope. So this is the extensive form game diagram. Let me also highlight the parts which are continuous like I did last time. This just highlights this as. Okay, so now let's go over the rationale, right? So in the last period, the last stage, player 2 is the one who's making the final offer. So when player 2 is going to make an offer Z, he's going to offer Z as 0, right? He's not going to want to offer anything more because the player 1 only has the choice between 0 and delta square Z. So he's indifferent between choosing both, whether he's offering 0 or not offering anything. I mean, if he's offering something more than 0, he's obviously going to accept, but he knows that he'll accept even if he offers 0, right? So Z is going to be 0 in the final stage. We're doing backward induction. So by backward induction, in stage 3, player 2 offers Z equal to 0 and keeps delta square into 1 minus Z equal to delta square as payoff, right? This is the final payoff to player 2. Now, player 1 knows that player 2 is going to offer 0 in the last stage, and player 2 is going to get delta square as payoff. So what player 1 will want is that in both the stages, in stage 1, stage 2, stage 3, this is 1, stage 2, and this is stage 3, right? So in stage 2, he will want player 2 to accept so that the game doesn't go to stage 3, so that player 1 can also get some positive payoff, right? So in stage 2, player 1 will offer Y such that delta Y is equal to delta square, which implies Y is equal to delta, right? He's going to offer something which is so that player 2 is indifferent between accepting and rejecting, because player 2 knows that if he rejects in the next stage, he's going to get delta square, right? So Y becomes equal to delta. Now player 1 does even more forward thinking, and player 1 knows that in second stage, player 2 is going to accept Y equal to delta. So in stage 1 itself, player 1 will offer X such that in stage 1, the payoff of player 2 is X, right? He will want X to be equal to delta Y because he wants player 2 to accept, right? So X is equal to delta Y. And what is Y? Y itself is delta, so is equal to delta square, right? So in stage 1 itself, player 1 is going to offer delta square so that player 2 accepts in first stage and both get a payoff of 1 minus delta square and delta square. And of course, then the game does not need to proceed to the next two stages. Therefore, SPNE is that player 1 offers X is equal to delta square and both get payoff of 1 minus delta square comma delta square respectively. Okay, so in the solution to this question, if you look at the solutions, I think they're messed up somewhere on the notation because they are reporting a flipped answer of 1 minus delta square and delta square. So somewhere they have messed up on the interpretation of X, Y, or Z or something. I don't know in what stage they messed up, but I'm just saying that that is likely. Otherwise, I think the result is not so difficult to arrive at. Okay, so I don't think you will get questions which are much more complex. The infinite form of the bargaining game is already discussed in the lecture, so I didn't want to take that up. It's a slightly different question because the offers are not alternating like that. So I thought I'll take this question. So, any other doubts here? Sorry, I didn't understand your question. What would the answer have been if second stage pair was not pair one, the another offer? Is that why the answer is different? So yes, the answer is going to be different if in this game you had first stage player one is making the offer, second stage player two is making the offer, third stage player one is making the offer, like how you normally have in traditional bargaining questions, then the answer would, I think the answer would be different. I think in those cases, the answer is something like delta into 1 minus delta or something. I mean, I've not memorized it, but offhand, I think that is the answer. In this case, because it's not alternating like that, the answer comes out to be delta square. Is that what you were asking? Okay, so I think you had asked some questions on the discussion forum also. Let me just open that. So, okay, one was for the perfect Bayesian equilibrium, and the second was about cooperative game theory. So, if you send me the actual research paper which you're referring to of the Stackelberg game, I can answer this, but there's no, I mean, what you've asked is a very general question, so I'm not sure what you are referring to. So, I don't know if I can answer it without knowing the question itself. But in general, cooperative game theory refers to games such as the bargaining game, in which there is some quantity, some surplus or some revenue or something, which is achieved by cooperation between two players, right? So say suppose there are, n players, n laborers maybe, and they all need to work together to achieve a certain output, Y, okay? And then they decide how to split that Y between each of them. And each one of these n players is still maximizing their own payoff. It's not that they're maximizing something else, they're still maximizing their own payoff, but the output Y is obtained only by the cooperation of all of these players. And this is sort of like what we do in the bargaining games. Now, this type of game theoretical modeling is used in all sorts of different situations. But that is the basic form, that is the basic structure of cooperative game theory. So I don't think we have covered sort of cooperative game theory on its own in the lectures anywhere. So I don't want to like dive too much into it. But if you want, you can read up a little bit on cooperative game theory. I think you will find some class notes and stuff on cooperative game theory in some of the online MOOCs by universities, where they have like slightly more advanced treatment of game theory. So there they have like this. It's a bit more mathematical, their lecture notes and stuff like that. But you will get an idea of what is cooperative game theory. If you want, you can let me know your email. I will send you some notes on cooperative game theory from one of the online MOOCs. Okay, so this is that. Now I will just go through the perfect Bayesian game, and I'm not like taking the whole literature of the game. This question I'm taking from the Felix Munoz Garcia book. It's an example in chapter 9. And I've changed the notation a little bit in this question. This is a diagram from the book. But the types assigned to player 1 are mentioned as something else, which is a bit confusing. So I've just mentioned it as G or B, which you can think of as girl or boy or good or bad or whatever you want to think of it as. So this is the game in which first nature acts and assigns a type to player 1, G or B. Then player 1 acts, and if it's of type G, they have the choice to play L or capital R. And if they're of type B, they have the choice to play L prime or R prime. If they play L or L prime, the game ends and they get a payoff of 2. Everybody gets a payoff of 2 comma 0. That's the final payoff. If they play R, then or R prime, then player 2 acts, and player 2 has a belief Q about player 1 playing R, and hence the belief about player 1 playing R prime is 1 minus Q. So Q is player 2's belief about what strategy it's facing, whether it's facing R or R prime. And in either scenario, player 2 has the options of playing U, comma D, U or D. And the payoffs are as shown. And of course, both the players know their own type. Player 2 doesn't have another type, it has only one type. Player 1 can be of type G or type B, and the probability of nature selecting type G or type B is half. This is the prior. This is what we call as the prior probability in Bayesian, Bayesian literature. Now, Q is 2's belief about what the type is actually, right? What type he's actually facing. So the question is to find all the pooling and separating equilibria. And again, I'll give you a few minutes to first, redraw the diagram if you want, find the strategies if you want, or just think over it a little bit. And then I will solve the question. And I will try to go a bit slower in this question because, Bayesian, perfect Bayesian equilibrium is a slightly abstract concept. And I don't think it's very useful to sort of rush through it. So I'll mute myself for a few minutes and I'll also get some water. I'll be back in like 5-10 minutes and then we'll discuss this question. Okay, so any ideas or questions? Were you able to get started? No, okay. No is for question and no is for not able to start it. Okay, all right, no problem. I'll explain it. So your question, I think you had posted a question about the lecture on obtaining perfect Bayesian equilibrium also. So okay, let's get into it. Okay, let's draw this diagram again in the slides. Let me open this here. Okay, so let me just draw this diagram again and explain what is happening and what exactly we mean by separating and pooling equilibrium. So I'm just drawing it in a neat way, but I'm not drawing it sequentially. Okay, so let's start here. So this is the first node, the one I've drawn. This here, you can say that nature is acting here and selecting a type for player 1. Okay, this is player 1. This is type G and this is type B. And nature is selecting the type for player 1 with probabilities half. You can say this is P. Okay. P is the probability with which nature is acting. And when you reach the node L or L prime, the payoffs are 2, 0 here and 2, 0 here. Now, if instead of L, player 1 can choose R also, or in this case R prime. So if it's of type V, player 1 chooses R prime or L prime, and if it's of type G, player 1 chooses L or R. Now we have a player 2 here, and player 2 is not aware of the type. A priori, player 2 is not aware of the type of player 1. Without knowing the type of player 1, he has to choose between U and D. And the payoffs are this for. Okay, so this is the diagram. So at least, have you understood the game? What is the game exactly? What is happening in the game? Okay, so now we are talking about a perfect Bayesian equilibrium in which we are trying to find out two types of equilibria. One is the separating equilibria and one is the pooling equilibria. So first, let's talk about the separating equilibria because that is a little bit easier to understand and rationalize. So let's first focus on separating equilibria or equilibrium, whatever you want to call it. Okay. So separating equilibria is when you understand or you understand or you know the type of the first player at equilibrium. Okay. Now this happens when, so if, for example, like you're, say suppose you are in a business and you don't know what was the type of your other player. Let's say G and B are good and bad. Okay. Now if in some situations it may happen that you know that if the other player is of type good, they're going to take action R, whereas if they are of type bad, they're going to take action L or L prime, right? Or the other way around, that if the player is good, it's going to take action L, and if it's bad, it's going to take action R prime, which means that different types are taking different actions. That is what we mean by separating, meaning that the type of the first player gets revealed in equilibrium. So that is what we're calling as separating equilibrium or equilibria. So the two possible, we're not saying this is an equilibrium just now. We are saying that there are two possibilities for separating equilibria, which is L and R prime and L prime and R. So in two ways, you can get a separating equilibrium, which means that in equilibrium, the good type player is playing L and the bad type player is playing R prime, or another equilibrium in which the good type player is playing R and the bad type player is playing L prime. Is so far so good? Is this clear? Is this understood by you at least? Then I'll move forward from there. If not, you can tell me. I'll explain in some other way. Okay. So now we come to the belief of player 2. So we are using a notation Q to define player 2's belief about which node has been reached. Now see, player 2 is in this dotted line space. Okay. Player 2 doesn't know which type the other player is, hence player 2 does not know if he has reached node R or if he's reached this node after the player 1 has played R or R prime. But what happens in separating equilibrium is that in equilibrium, if, say, suppose we're talking about the first equilibrium, okay, taking the possibility of L R prime as equilibrium. Okay, we're considering this possibility. We're not saying this is an equilibrium, which means that in equilibrium we are assuming that L and R prime is played by player 1. Now, if L and R prime is played by player 1 in equilibrium, then player 2 knows which node is reached, right? If R prime is getting played and L is getting played in the final equilibrium, he knows that the player 1 is of type B because R prime is reached only if player 1 is of type B, right? If R prime gets played, player 2 knows that player 1 is of type B, right? Because only type B is going to play R prime. Type 1 or type G is playing L in equilibrium. So if at all player 2 has to take a decision after R or R prime and he knows that the node R / R prime is reached, then he knows that it is reached only if player 1 is of type B. It is not reached if player 1 is of type G. Therefore, his belief about which node is reached is no longer a belief. He knows with certainty that 1 minus Q is equal to 1, right? Therefore, 1 minus Q is equal to 1 or Q is equal to 0, right? This is just an extension of what I just said. If R prime gets played, then the type of player 1 is revealed, which means 1 minus Q is equal to 1. With certainty, he knows that he is at node number 1. Now, if he is at node, not node number 1, with certainty he knows that he is at node followed by R prime. And Q is equal to 0. Now, if Q is equal to 0 and he knows that he is at this node, okay, or let me circle it in some other color. If he knows that he is at this node, right, the green annotation, then he is going to choose between his strategies U and D. Now, between U and D, he is going to choose D because this gives him a higher payoff, right? If this happens, if this part of the game gets played down, now player 1 of course knows his own type and he knows that if he plays R prime, player 2 is going to choose D, right? So if player 2 is going to play D, then what is the payoff of player 1? Let's mark that also on the diagram. Player 1 is getting 1 in this scenario, and if he plays L prime, he's getting 2, right? So 2 is giving him a higher payoff. So he's going to want to play L prime instead of R prime, right? Player 1 is going to want to optimize his benefit, right? No, that is the original supposition which we started with, that he is playing L comma R prime. We'll come to that. Let me first finish this part of the game. I have not reached the part of the game where we are comparing between L and R. Okay. First stick with this rationale. I think what you're not understanding is the backward induction. What we're doing is backward induction right now. We started with the proposition that L R prime is an equilibrium. Now we are checking if it is an equilibrium. Okay, so we are saying that player 2 knows with certainty that R prime has been played. He is taking Q as equal to 0. Then he is deciding his strategy. So he has decided that he is going to play D. Now player 1 is doing the thinking part. He is seeing that if he plays R prime, player 2 is going to choose D. And if player 2 plays D, so this is how we calculate subgame perfect equilibriums, right? We do backward induction. So if player 2 is going to choose D, player 1 is going to get 1. Whereas if he plays L prime instead, he is going to get 2, right? So he's not going to play R prime instead in the actual game. He's going to play L prime. That's giving him a better payoff. So that means that this strategy, it cannot be an equilibrium. We are checking in this process. Okay. Now let's go to the other part of the game. Now we are assuming that player 2 has chosen D, right? So which means that even in the other part of the game, he is going to choose D because he has taken Q as equal to 0. So his strategy still remains as D. Now in this part of the game, let's see what happens to player 1's payoff. If player 2 is choosing D, player 1's payoff is 1. Whereas if player 1 chooses L instead of R, his payoff is 2. So he is going to want to choose L. Not this color. He is going to want to choose L here also. Right? So this means that the part where we said R prime can be an equilibrium, L part is correct, but R prime is not correct, right? Therefore, L R prime is not an equilibrium. Now, all this what I've explained in words. It's a lot to write down, but I'm just writing it in 1 or 2 lines here. So all this explanation is given in great detail in the book, from which I've taken this example. If you want, you can read that for your further clarity, right? Therefore, L R prime is not an equilibrium. Because even though the L part is correct, the R prime part is not actually happening in the game. Okay, so this was one of the separating equilibrium. Now we move to the other separating equilibrium, which is L prime comma R. Highlight this or something. Now we are saying that we are checking. First we have done L R prime. Now we are doing L prime comma R. Okay, so now let's go back to the game. L prime comma R. Okay. Now L prime comma R means what? That if R is played, then player 2 knows with certainty that the type of player 1 is G, right? He's only if type is G, R is getting played. Otherwise, it's not getting played. You're understanding? So if you go back to the gift game, it is equivalent to saying only if it's a friend, they're going to give a gift. If it's an enemy, they're not going to give a gift. Similarly, here player 2 is saying that if only if the type of player 1 is a good guy, he's going to play the strategy R. Otherwise, he is going to play the strategy L prime. So if R gets played, he knows with certainty that player 1 has type G. Therefore, Q becomes equal to 1. If Q is equal to 1, let's see what happens to the payoff of player 2. If 2, let me erase these for now. So I'm erasing these because I don't want to sort of confuse you in this part of the game. I'm erasing this part. I mean, in the book, if you refer to the book, this whole game is drawn several times with different, arrows marked. So if you want, you can refer to that. It will help you understand it a little bit better. But in my diagram, it's going to mess up the diagram and I can't draw the diagram 5 times. So I'm just erasing these annotations. So now if player 1 is playing R and player 2 knows that player 1 is playing R with certainty, he's going to now choose between U and D. Now strategy U is giving him a payoff of 2, whereas strategy D is giving him a payoff of 0. So he's going to play strategy U here, right? If player 1 puts his thinking hat on. Now player 1 knows that if he plays capital R, player 2 is going to choose strategy U. Now, if player 2 is choosing strategy U, player 1 is getting a payoff of 3, right? Whereas if he chooses capital L as a strategy, he is getting a payoff of 2. So it's in his best interest also to play strategy R, sorry. This is the direction in which the game is going to proceed. Hence, this part of the game is perfect, where he is going to choose R and player 2 is going to choose U. Now let's see what happens in the other part of the game. Here also now player 2 is anyways choosing U. Okay, he has decided Q is equal to 1 and he is choosing U. Now in this other part of the game, continuation game as we call it, if player 2 is choosing U, player 1 is getting a payoff of 1, right? Whereas if player 1 chooses L prime, he is getting a payoff of 2. So he'd rather choose L prime. Hence, this part of the game is also fine. This part of the game can also proceed because that is what we were checking. Is L prime R an equilibrium? Therefore, both R and L prime turn out to be the proper strategies, subgame perfect strategies in equilibrium. And I'm just going to write this down again. Player chooses U, right? Sorry, 3, not 2. In the second game, in the other continuation game, for strategy U by player 2, player 1 gets 1. Therefore, L prime R comma U is an equilibrium. So have you understood the rationale so far? In a separating equilibrium, so player 1 gets 1 for playing R prime. Now you look at this diagram. In this diagram, if player 1 chooses R prime, he's going to get 1, right? Because player 2 is choosing U. So payoff of player 1 is 1. That is what I'm saying. Whereas if player 1 chooses L prime, his payoff is 2. I've circled 2. Yes, because player 2 is anyways playing the strategy U. Now player 1 is thinking between L prime and R prime. If he plays R prime, player 2 is going to choose U and he's going to get a 1. If he plays L prime, he's going to get 2. So he's obviously going to choose L prime. So the same logic we have always used in backward induction. Okay. And hence we find that in the second part of the second continuation game also, L prime is actually an equilibrium strategy. Therefore, L prime and R both are equilibrium strategies, and L prime R comma U is the separating equilibrium. So far so good. Okay, so now this is the two separating equilibria. Let me just keep the diagram in the front for now. Now let's talk about the pooling equilibria. Pooling equilibria is when, irrespective of the type, both the players are choosing the same strategy, right? So in this case, that is if player 1, whether player 1 is of type G or of type B, he is playing the same strategy, which is R and R prime or L and L prime. So there are two types of pooling equilibria. It's like messy by now already, but anyway. There are two types of pooling equilibria, which is L prime and R prime. L prime is when both types play the strategy L or L prime in equilibrium, and R prime is when both the types play R or R prime in equilibrium. Now there is one fundamental difference between separating and pooling equilibria, which is that in separating equilibria, you immediately know the value of Q, right? Because you know which node is you have reached, and hence you know the type of the player 1. Whereas in pooling equilibria, you don't know that. In pooling equilibria, you are not sure of which node is reached, because either way, whichever node gets reached, you are facing the same strategy. So in this case, let's start with first, like just explaining, first just discussing what is actually happening here. So let's take the, let's take R prime first. We'll come to LL prime. Now in the case of R prime, the player 2 does not know which node is reached, right? So in this case, what he's going to assume is that Q is equal to P, because he does not have any reason for having prior belief, right? He assumes that Q is equal to P because he has no reason to believe one way or another, right? He's not getting any new information after player 1 has played the strategy. See, in the separating equilibria, after player 1 has played the strategy, player 2 updated their belief with Q, with the value of Q is equal to 1 or 0 or whatever, because he knew that based on what strategy has been played, he knew which type the player 1 is. But in a pooling equilibria, that is not the case, right? So in the case, we'll come to LL prime later and you will understand why later. But when R or R prime is played, he knows that one of the two has been played, R or R prime, but he doesn't know which one. Now in that situation, he knows that because the player 1 has played R or R prime, the probability Q is going to matter. It is not that it is not going to matter. Look, when the player 1 plays L or L prime, player 2 is not taking any action, right? And he doesn't have any strategy in that case. So in that case, the probability Q or the belief Q of player 2 does not matter. But when player 1 is playing R or R prime, player 2 has to take the next action, right? So in that case, his belief Q does matter. And because he has no new knowledge about whatever has happened and what the type of player 1 is, he is going to take Q as equal to P. So let me write that down. Taking R prime as a possible equilibrium. Yeah, like this also. Now, in this case, player 2 takes, player 2 has no new information. Therefore, P is equal to Q is equal to half. Okay, we know we are given in this particular question, we are given the value of P, which is equal to half, right? So now, what is player 2 going to do? What we normally do in a Bayesian game or in these type of games. What is player 2 going to do? He is going to calculate his payoff for either strategy. If he chooses if he chooses U, his payoff is going to be, let's look at the diagram. The payoff is for strategy U, it is Q into 2 plus 1 minus Q into 0, right? And for strategy D, I don't want to keep scrolling. So maybe I'm doing this a bit late, but let me upload the slides in the folder itself so you can look at it while I'm explaining. I think it's a bit annoying to keep scrolling back and forth. So give me one moment. Let me just upload this first so you can open the slides on your system alongside. Okay, so if you check the shared folder, I have uploaded the slides PDF in the shared folder. Yes, it is given. The value of P is given in this question. So it will not always be given, but in this case, P is given as half. If you look at the diagram, I've shared the folder, I've shared the slides now. If you look at the diagram, you can see half and half is written over there in the diagram, which means that the value of P is equal to half. Did you get that? Did you find the slides? This is the folder. I just put the link on the chat where I've uploaded the slides. Yes, the value of P is common knowledge. Okay, so P is the probability with which nature is choosing the type for player 1. But Q is something else. Q is player 2's belief about which node is reached. Right? So in a situation where it's a pooling equilibrium, he does not know which node is reached in the final equilibrium. And hence P and Q become the same. Does that answer your question? Okay, so let's continue with the game. I'm not scrolling up to the diagram because that's why I shared the slides. It's a bit annoying to keep scrolling up and down. what we were doing is that player 2 is considering the possibility of R prime as the equilibrium, and he is assessing what his payoff would be for strategy D this time. So if he's playing strategy D, his payoff is 0 into Q from the first continuation game, and 1 minus Q into 1, 1 into 1 minus Q. It is equal to 1 minus Q in the second continuation game. Right? Now we can calculate this because we know the value of Q. This is equal to 1 and this is equal to half. Right? Because we just wrote here that P is equal to Q is equal to half. So we know the values of the payoff for player 2. So which means that player 2 is going to choose U, right? Player 2 is getting a better payoff for U, so obviously he's going to choose U. Now, if player 2 is going to play U, now remember, player 1 already knows his type. If player 2 is playing U, and consider the first part where he is of type G, player 1 is getting a payoff of 2 for the strategy U, and he's getting a payoff of U for strategy L. So he's going to choose strategy L. Let me again mark this on the game actually. As before, I'm erasing this initial annotations. Obviously there in the live session. So I'm just redoing this part. Player 2 is playing U. Now player 1's payoff for player 2 choosing U is 3 here. Player 1, right? So 3 here, and for strategy L it is 2. So player 1 prefers to play R, right? Now in the second continuation game, what is happening? If player 1 is playing U, the payoff of player 1 here is 1, right? This is 1, and in L prime, if he chooses L prime, his payoff is 2. So he's going to choose L prime instead. And hence, R and R prime is not an equilibrium strategy because he's not choosing R prime in the second continuation game. Therefore, we conclude. Now, writing this is a bit tricky, but okay. Player 1 gets payoff 3 for strategy U of player 2 in the first continuation game, but in the second continuation game he gets higher payoff for L prime, not R prime. Therefore, R prime is not an equilibrium. Okay. We have only one more equilibrium to check, but I'm just going slow just because this is a slightly different kind of a concept. We first start with some assumption about what can be a possible equilibrium. Then we check if that is actually an equilibrium strategy for both the players by backward induction. So RR prime turns out to not be an equilibrium. Now let's move on to the next one, which is LL prime. Okay, so now in LL prime, you remember in LL prime there is no sort of action for player 2. LL prime is a strategy by player 1 in which the payoffs of both the players are determined just after player 1 plays the strategy L or L prime, right? So here, let's see what happens. So in this case, Player 2 has no idea, no information at all about what is actually happening in the equilibrium, as in which type player 1 is in the equilibrium. So he has no new knowledge, and also because the player the strategies of player 1 are L and L prime, there is no reason for him to believe whether P is true also or not, because P is the probability with which player 1 is selected as G or B. But once he's selected as G or B, he plays R and R prime, and then player 2 acts. But L and L prime, the payoff is the same for both of them. But there is no action for player 2, and he does not know he doesn't have any information about player 1. So in this case, he's not going to take Q as equal to P. That is the main important understanding. Here, player 2 has no direct action, and therefore he has no prior for Q. Right? So in this case, we are not going to take Q as equal to P. So Q is some unknown value in this part of the game. Okay. So now let's consider what the different possibilities are. So please open the diagram on your system if you can. Now let's see what happens. We are again going to calculate the payoff of player 2 like how we normally did. Now let's considering payoffs of player 2 in both the possibilities, in both the continuation games, and then we'll compare. For strategy U, his payoff is, we just calculated 2Q plus 0 into 1 minus Q is equal to 2Q. And for strategy D, his payoff is 1 into Q, sorry, 1 into Q plus 1 minus Q into 1. It's equal to 1. Okay, so this is where we're at. Now we are going to compare the payoffs of both the players in both the scenarios, right? For why will it be 0 into Q? No, the first term is not 0. Oh, sorry, yeah, we're taking payoff of player 2, right? I made any other mistake? No. Okay, 0 into Q plus 1 into 1 minus Q. So this is 1 minus Q. Okay. So if he's just indifferent, or let's not take indifferent case, let's just directly go to if 2Q is greater than 1 minus Q, he chooses U, right? So which means, let's take Q this side, 3Q is greater than 1, Q is greater than 1 by 3. So if Q is greater than 1 by 3, he chooses U. If Q is less than 1 by 3, player 2 chooses D. If Q is equal to 1 by 3, he is indifferent. Okay, this is simple. This is what we are used to doing. We just calculated the payoffs of player 2 for both the strategies as a function of Q, and then we checked when he gets a higher payoff for playing U versus when he gets a higher payoff of playing D, and we got a range of values for Q. Now we're going to go back and look at the payoffs of player 1, right? We have still not considered the payoff of player 1. This is just understanding what is happening for player 2. Now we'll look at payoffs of player 1. Now, if player 2 chooses U, okay, first case, that is, which means Q is greater than 1 by 3. We just wrote that he's choosing U when Q is greater than 1 by 3. Or let me put this arrow here. If player 2 is choosing U, no, it's not less than 1 by 3. Right? Okay. So if player 2 is choosing U, let's look at the diagram. Yeah, I'm erasing the annotations from before as usual. Okay, if player 2 is choosing U, now let's look at the first part of the continuation game. Player 1 is getting a payoff of 3 for playing R and 2 playing U, and he's getting a payoff of 2 for playing L. So player 1 would rather play R, right, because he's getting 3 here. And in the second part of the sub game, or sorry, not sub game, continuation game, if player 2 is choosing U, that is, if player 1 is playing R prime and player 2 is choosing U, player 1 is getting payoff of 1, whereas for playing L prime, the payoff is 2. So he is going to choose L prime because here the payoff is 2, right? So we cannot have L prime as in equilibrium because in the first part of the continuation game, he is choosing a strategy R, right? He's not choosing L. That is for the case when player 2 is choosing U, right? So in this case, let's write this down. So in this case, if player 2 is choosing U, player 1 gets higher payoff for R in first continuation game. Therefore, L prime cannot be an equilibrium, right? Now let's consider the other case, right? If player 2 chooses D, that is Q is less than 1 by 3. Let's look at this again. If player 2 is choosing D, in this case, player 1 is getting a payoff of 1 for choosing R and 2 for choosing L. So he's going to choose L, right? And in the second continuation game, also if player 2 is choosing D, that is, if player 1 is playing R prime, he gets a payoff of 1, whereas for L prime, he gets a payoff of 2. So he's again choosing L prime. So if player 2 is choosing D, that is, if Q is less than 1 by 3, L and L prime can be an equilibrium because in both the cases, in both the continuation game, player 1 is choosing L and L prime. Player 1 So you have to write the whole thing, L prime comma D for the value of Q, which is the range we have taken, Q less than 1 by 3 is an equilibrium. Now, we should also consider the case of when Q is equal to 1 by 3, which means where player 2 is just indifferent between choosing U and D, right? If player 2 is indifferent between choosing U and D, no. Okay, I forgot this part, how we solve it. Just give me a moment. I think I may have missed this part. I think you take an average. Sorry. They have, I don't know if they've even discussed this. Yeah, even they have not discussed this actually. Funny enough. So let me just think over it, because it only just occurred to me that we have not taken the case of Q equal to 1 by 3. And I am a little bit unsure of what happens if Q is equal to 1 by 3. Because if, if player 2 gets indifferent between choosing U and D, then what happens to the payoff of player 1? I'm not exactly sure of. So you can take, I think maybe from what I remember beforehand, roughly remember, is that you take an average. If you take the average payoff, 3 and 1 average is 2. So 2 and 2 is, you compare 2 when he plays R with 2 when he plays L. So that is 2, he chooses L. And U comma D, he gets average of 1 because his payoff is 1 and 1. So if he plays R prime, he gets 1. If he plays L prime, he gets 2. So L prime is again an equilibrium. Again, I'm writing this because I think this is how it is, but I'm not exactly certain. So I will post a note on the discussion forum afterwards once I've just checked this, because this is not given anywhere actually. If Q is equal to 1 by 3, average payoff of player 1 when he plays R is 2 and L is also 2. Therefore, both are best response. And when he is of type B, L gives higher payoff. Therefore, L prime comma R, not R, sorry, U, and L prime comma D are both equilibria for Q is equal to 1 by 3. Again, I'm not exactly certain of this last case where Q is equal to 1 by 3 and player 2 is indifferent between U and D, but I think this is how it should be. So I will check this part and I will let you know whether I'm right or wrong. If I'm wrong, I will correct this part. Any questions? Is perfect Bayesian equilibrium clear to you now? So we got two perfect Bayesian equilibria, I think. L prime for the case when Q is less than 1 by 3. Let me highlight this. And the other one was, I think, L prime comma U, which is the separating equilibrium. So we have two equilibria in this particular case. It may not always be the case. Sometimes you may not have any equilibrium for that matter. But yes, so this question is solved in the book, and they have given it step by step. There is an explanation there. I mean, I'm following the process we discussed in the class. So I have solved it using the same rationale as what Professor Vimal has discussed in the lectures. But they have given a similar kind of a thing in the book. I've not gone over it in a lot of detail, but I just saw that they have given some steps to calculate it. and the method is not too different from ours. So if you want, you can read it. It's explained pretty clearly, I think, in the book. And I didn't find a very good explanation of perfect Bayesian equilibrium in other books. So, of course, Joel Watson has it, but it's the same question as what Professor Bimal has discussed in the class. So, I mean, if you want, you can read it. It's explained in Joel Watson also. But in all the other books, I didn't find something which I thought was too good. So, I didn't use any of those examples. So, there are examples for this concept in both these books, especially Joel Watson has quite a few exercises in the end. I'll encourage you to practice, because see, the logic we use in separating equilibria and pooling equilibria is slightly different, in the sense that, you know, everything hinges on what we are taking the value of Q to be, right? And the way we calculate Q is, you know, the main subtlety here. And when after we calculate Q, what we are doing in this entire process is we are calculating the payoff of player 2 first, because we're doing backward induction. And based on the payoff of player 2, we are ascertaining what the strategy of player 2 is. Then, when we know the strategy of player 2, we are seeing whether player 1 is actually playing his best response or not in the assumption we have made in the beginning. Right? Like how in maths problems you have to prove x square is equal to y plus 1 or something like that. You start with assuming that, and then you check the values of x and y, and then you come back and see whether x square is equal to y plus 1. So we are doing something like that in this case. We see whether player 1's strategies, which we had assumed in the beginning, they are actually his best response or not, based on the strategy of player 2, which we just calculated. Okay, so that is the 1 line or 2 line summary of what we do. But of course, there is a lot to think over here, because in the value of Q, the way we calculate it in pooling equilibria and separating equilibria is different, and the rationale we use is a bit subtle, you know, so it's not that obvious sometimes. It is, yes, it is a slightly involved process, which is why I don't think they're going to give you a very difficult question on this. But I mean, it's an important concept to understand. So I hope you have at least understood the concept of perfect Bayesian equilibrium. Okay, great. So I will, of course, upload everything by end of day. And if you still have any questions remaining, and also about that question you were asking me about Stackelberg in the discussion forum, if you post the paper or if you send me the research paper, I can tell you my thoughts on it. Otherwise, we'll end the class here. And I hope you had a good time learning in this course. It's a really good course. And if you have any other questions from the course, you can of course post on the discussion forum, or you can email me. And also you posted something about the exam format, right? So the TA will answer. I've checked with them. They will respond to your queries. Okay. All right then. It was really good for me also to teach this class. And I'm glad that you found some help with the TA sessions. So thanks a lot, and all the best for your exam.